Hello everyone, my name is Neha and this is the sixth lecture on electronic circuits. In this lecture, we're going to see two different types of thyristors. We will learn about triacs and unijunction transistors. And in the last lecture, we covered diacs and SCRs and their characteristics. So let's begin with the triacs. Triac is a bidirectional thyristor which is used to control the power in AC circuits. A triac has two leads designated by name MT1 and MT2, or you can say anode 1 A1 and anode 2 A2. And triac can conduct in either direction. It has a gate lead which is used to control its conduction, and a triac is equivalent to two SCRs in parallel. So if you remember from the last lecture, the SCR, it conducts only in one direction, right? So just imagine if you put two thyristors together in a parallel, connected in parallel, then we can obtain the conduction in both the direction, and that's what the triac is. So let's see the construction of the triac. So this is the schematic symbol of a triac, and there are two anodes in this, anode 1 and anode 2, and then there is a gate lead here. And this triac is equivalent to two SCR connected in parallel, and that you can see in this circuit B, where these are the two SCRs, and this is the gate lead, and these two gate leads are connected. Okay, and these are the two terminals, anode 2 and anode 1. And you can see this is the same replica of this symbol. So you can say that the triac is basically equivalent to two SCRs connected in parallel. Now, there are four operating modes in triacs, and these four modes are given here. A2 basically stands for your anode 2 terminal, and this says like what will happen when this anode is positive with respect to the gate. And we will see all these four different modes. So when the anode is positive, so these are the two cases when anode is positive, then what happens when the gate is positive and negative, when anode is positive. So when an anode is positive and then gate is positive, then that is considered as your first mode. And this mode requires less gate current. And when you have A2 is positive and gate is negative, then this is called your second mode. And when your A2 is negative, you're providing negative supply to A2 anode, and your gate is positive, then you will be in the third mode of operation. And in these two and third mode, in these two modes, the gate, it requires higher gate, the triac requires higher gate current to trigger. And then you have this last mode when your A2 anode is negative and your gate is also negative, and that is your fourth mode. And in this mode, the triac requires less gate current. And so we saw that in this case, this is the sensitive case where requires less gate current, and this one also less gate current, but this is more sensitive. And in these two modes, the triac requires higher gate current to trigger. And sensitivity of each of these modes is also dependent upon the temperature. So as the temperature of the device increases, the gate current may decrease. And triac requires different gate currents for each mode of operation. So triac may not trigger at the same point for each alternation of the input cycle. So therefore, here comes the use of the diac, that we use the diac in conjunction with the triac to ensure that the triggering time for the triac is same for all the modes. Okay, when it is working in both positive and negative alteration of the applied voltage. Now we are going to see how we can use the diac in conjunction with the triac. As you can see in this particular circuit, we have a diac which is connected to the triac here, and this diac is responsible for providing the symmetrical triggering to the triac. And why we picked diac for this particular circuit, why this diac has been picked to provide the triggering to the triac? The reason is that if you remember the characteristics of the diac, and if you see that, then you will see that there are two breakdown voltages in the forward and in the reverse direction, and those after reaching to that breakdown voltage, you can provide the conduction, right? And that can be done on both the sides, positive and the negative, and that's the reason we are using here. Okay, so here we have 120 volt AC and 60 hertz is going in here, and this is and then this is, you have the resistor R1, and this has a wiper connected, and then this is the load resistance, and this is kind of forming like a RC phase shift. It's providing a 180-degree phase shift. So you can read here also, RC1 and RC2 provide the required phase shift necessary for full control of the load's current. And as you increase or decrease the R1, you can control the load current. So this will provide the triggering, and based on that, the voltage to the load as you increase or decrease the load resistance. And this, instead of this resistance, you can also use pulse DC, and then that can also provide a particular point where you can basically stop the conduction or start the conduction. That also you can use. So this is triac, and this is one of the example. Now let's move on to unijunction transistors. So unijunction transistor, it is a 3-terminal semiconductor device that has only one p-n junction, and the unijunction transistor has two base leads, B1 and B2, and there is an emitter lead, and the interbase resistance RBB, which is in between the base and the emitter lead, that's called your RBB of a UJT, is given by is the resistance of the n-type silicon bar. So we're going to see the construction and how it looks like in the next slide. And the ratio of those two base leads, B1 and B2, the resistance they have inside it, their ratio is given by this RB1 upon RB1 plus RB2, where this is called your intrinsic standoff ratio, and sometimes denoted by eta. So this is the eta sign. And UJT is used in conjunction with the SCRs and triacs to control their conduction angles. So similar to triac, you can use the UJT, which can help in providing the control on the conduction angle. Okay, so this is the construction of UJT. As you can see, this is the base, and this base is made up of ceramic, and each piece of base is bonded by a gold film to each end of the silicon bar. And this thus forms a low resistance contact, which is called your ohmic contact, which you see here is the ohmic contact. And then you have this n-type silicon bar, which is lightly doped, and it has a resistance value between 5 and 10 kilo ohm. And then you have this p-type material, which is called your emitter, is placed closer to, mostly if you see, it is placed closer to the base 2. So this base 2 a little bit up than compared to base 1. And the same you can see in this symbol also. So this is the emitter, which is placed closer to base 2, and this is base 1. And this is the circuit diagram for UJT. This is the emitter, and this is shown by a diode, by this diode. And then you have this B2 and B1 terminals, and each has some resistance, and these are called your interbase resistance. So the total resistance, total interbase resistance, which is you can say RBB, and that RBB will be equal to the sum of these two resistances, which is RBB is equals to RB1 plus RB2, and that will be, so this total resistance will be equal to RBB only when the emitter current is 0 here. So when you have 0 emitter current flowing here, then you will have just these two resistance connected in series, and that the sum of that series resistance will be your RBB, and it's called interbase resistance. So interbase resistance I have not mentioned here, but you should understand that when your emitter current is 0, at that time whatever the total resistance is, that is your RBB. And this RBB, the value is dependent upon the doping level also, and the physical dimension of the this silicon bar. Okay, and then you have the voltage across RB1 resistance, and you can find that by using voltage divider rule. So which is equal to RB1 upon RB1 plus RB2, the sum of both resistances multiplied by the total voltage, which is a VBB. So VBB is given, which is the total voltage. So this was your equivalent circuit of UJT. Now let's see next. Now next we have the characteristics between emitter voltage and the emitter current. Okay, and in this you see there is a voltage VP here and then VV voltage, and what happens as the emitter voltage increases, when it reaches to this VA point, after that point your UJT will be turned on when it reaches to that this peak voltage point. And once the peak voltage is reached, then what will happen? We see a negative resistance region. What does that mean? It means that as the emitter current increases, the voltage is decreasing. So it is forming a negative relationship that when the after reaching to the VP point, this peak point, what is happening? Your emitter voltage is decreasing as the emitter current is increasing, and it reaches to this valley point, which is VV, given by this VV voltage. Once it reaches to this valley point, then what will happen? The UJT will go into the saturation region. So basically the emitter diode, it does not conduct unless the emitter voltage, which is VE, is greater than eta VBB plus VD. So that's we have got from the circuit. That means when it reaches to VP, then it will start conducting. Your UJT will be turned on. So in this region, you can also say that this is the active region when the UJT is turned on. Okay, and now let's move on to next. So this is the relaxation oscillator, which uses the UJT, and you see this is the UJT which is connected here, and these are the two base resistances, and then you have this RC phase shift connected here. So this CT is the capacitor which charges and discharges, and that charge and discharge we can see here from valley point to the peak point, peak voltage. The capacitor will charge and it will discharge from peak voltage to the valley voltage. From this, in this duration it will discharge. Okay, so this is the charging and discharging duration time. As you can, it is denoted by T. So the time required for the capacitor to reach to the VP is given by this formula. So this formula you will be using RT CT ln 1 by 1 minus eta. And what is eta here? So as I said here, that we have here eta is equals to VRB1 is equals to eta VBB. So this is some constant which will be given, the value will be given in the numerical problems if you attempt it. So we see here the increasing the value of either RT or your CT increases the time required for the voltage across the CT to reach the VP, because if you increase these two, they are directly proportional, the time constant will also change. And when the voltage across C drop to a valley voltage, then the UJT will be turned off and the and then cycle repeats, and that's what you see here. When it is dropped, then the cycle repeats, right? And the base one voltage waveform, VB1 is given over here, is the most important because it is used to trigger the SCR, or if you're using triac, then triac. And the frequency of the base one voltage waveform is the same as that of the emitter voltage waveform. Okay, so yeah, this is unijunction transistors, and this is the last topic in the thyristor. So that's the end of the lecture. Thank you so much for watching.